Hi, this is Rookie. Welcome to Math Key. Today we are focusing on a very unique type of algebraic equations. Guess what? Exponential equations. Before we begin, if this is your very first time of visiting this channel, subscribe for updates of recent videos. So let's dive straight into the topic. Let us take a few moments to understand what an exponent is before we start dealing with some sorts of exponential equations. In its simplest form, an exponent is the power to which any number or letter is raised. For example, if we raise 5 to the second power, then we say that the 2 is an exponent of 5, which is mathematically read as 5 exponent 2. Better still, 5 squared. Similarly, raising x to the 8th power means that x now has an exponent of 8. It is very important to know that another word for exponent is index, whose plural form is indices. So the words power, exponent, and index all have the same meaning. Note that the number at the lower part is called the base. Now that we have understood what an exponent is, what is therefore an exponential equation? This is a type of equation in which the variable is either the exponent itself or parts of the entire exponent. Other examples of exponential equations include these. In this video, we are going to learn how to solve the two most common types of exponential equations, the ones leading directly to linear equations and the ones leading directly to quadratic equations. Before we go straight into problem solving, we need to play around a few laws of exponents or indices for the sake of our beginners in this topic. This law states that whenever numbers are being multiplied in such a way that their bases are all the same, then we take one of the bases and assign to it the sum of the entire exponents to obtain 4 exponent 9. Hence, we can also write that 5 exponent 3x plus 1 is also the same as 5 exponent 3x times 5 exponent 1, which can now be written in this form, since 5 exponent 1 means ordinary 5. This law states that an expression of this nature, whose exponent is a product, can also be separated with brackets, since 3 times x is also 3x. Note that it is not out of place to swap the exponents whenever the need arises, since multiplication is commutative. Another way of writing the number 1 is raising any other number to power 0. In other words, any number raised to power 0 is also 1. Any number raised to any negative exponent is the same as 1 divided by that number raised to its positive exponent. In any given expression, what if the exponent is positive? Of course, the law also applies, but this time around in the reverse form. That is, the positive exponent now becomes negative, and vice versa. It is very important to understand that these laws also apply to all variables. For example, x raised to negative exponent 8 is the same thing as 1 divided by x raised to positive exponent 8. And p exponent 4 times p exponent 6 equals p exponent 10, and so on. Lastly, this is not one of the laws, but just a fact that we must know. In any given exponential equation, whenever the bases are equal, then by inspection, the exponents are also equal. Let us now apply these laws in solving a couple of examples. Like we did mention earlier, we are going to start from the simple examples to the complex for the sake of our beginners in this topic. The very first thing we want to do when solving any given exponential equation is to make all bases to be the same, if possible. At the right-hand side of this equation, 125 is a perfect cube. Therefore, we rewrite it as 5 to the third power, or 5 exponent 3. Since the bases are now the same, then by inspection, the value of x is 3. Let's look at another example still. In this case, the number 4 is a perfect square, whose value is also 2 to the second power. So we replace the 4 with 2 to the second power. Applying the law of power to both 2 and x, we have 2 exponent 2x at the left-hand side. Now that the bases are the same, then by inspection, the exponents are also equal. Therefore, 2x equals x minus 3, which is a linear equation. And collecting like terms, we have x equals minus 3. Let us play around another example to make sure that you understand what is happening. It looks like it's getting complicated, right? Don't worry. This is also as easy as the previous examples. Although 27 cannot be expressed in powers of 9, however, both 27 and 9 can be expressed in powers of 3. Since 27 can be expressed as 3 cubed and 9 as 3 square, we therefore replace each of them with their respective values. Applying the law of negative exponent to 1 divided by 3 cubed, we have 3 exponent minus 3. Even though the bases are now the same, we still need to clear off the brackets from both sides of the equation for the purpose of simplicity. And this can only be done by applying the law of power. So while the left-hand side becomes like this, the right-hand side becomes like this. We are now free to equate the exponents, thereby giving rise to this simple linear equation involving brackets. And clearing the brackets from both sides of the equation, we have minus 12 plus 3x at the left hand being equal to 4x minus 2 at the right hand side. So we just collect our like terms to have minus x as 10. Therefore, the value of x is minus 10 for this equation. You should be able to do this. Why don't you pause the video now and give this a try while I wait for you for a while. Welcome back. Let's check what your result is. 36 and 216 can both be written in powers of 6. Since 36 is also 6 to the second power and 216 is 6 to the third power, we replace each of them with their respective value. At the right hand side, we apply the law of negative exponent to 1 divided by 6 to the third power in the bracket to have 6 to negative exponent 3. Before we equate the exponents, we need to clear the bracket even though the bases are now the same. We apply the law of power to clear the brackets from both bases. Therefore, the left hand side becomes like this and the right hand side becomes like this. We now equate the exponents to get this linear equation. So we clear the bracket, collect like terms, and x equals 9. If you still find it a bit confusing expanding brackets or solving linear equations, maybe you need to visit our algebra playlist for help. We are diving straight into another type of exponential equation. This type is also called a disguised quadratic equation, in the sense that by careful observation, it can be expressed in the general form of every quadratic equation where a is not equal to 0. So the very first thing we want to do when presented with an equation of this nature is to look out for a way to express the first term in the form of ax squared, as it is in the general equation. And then we also look out for a way to express the middle term in the form of bx, just as it is in the general quadratic equation. Are we together? By careful observation, you will see that there is also a 4 exponent x in the first term. Let's see to that. 16 is a perfect square whose value is also 4 to the second power. So we gently replace 16 by 4 to the second power. Note that 2 to the fourth power also has exactly the same value as 16, but it wouldn't do us any favor to use it in place of 16, since what we have in the middle term is 4 raised to power something. So we use 4 raised to power 2. Since multiplication is a commutative operation, it will not be out of place at all to swap the positions of the exponents. Now we can see that there is really a common 4 exponent x between the first term and the second. Now that we have a common 4 exponent x, let's assume that 4 exponent x is equal to y. So we replace 4 exponent x to get this new equation, which is now the normal quadratic equation we all know. And after factorization, it becomes y minus 1 in bracket multiplying y minus 16 in bracket equal to 0. If you do not understand how we have factorized the quadratic expression at the left-hand side of this equation, then this video is certainly for you. It will guide you on how to factorize any quadratic expression in just one line. I'll put the link in the description below. Therefore, the roots of this equation are 1 and 16. Are these the final answers already? No. But relax. Just a few more steps away. We would have stopped here, but the question has not asked us to find the value of y, but rather the value of x, according to the original equation. Is that clear to you? So how do we find the value of x? Good question. Remember, there is a relationship between x and y. Therefore, we find the corresponding value of x for each value of y. And that means x will be having two values as well, since y already has two values. When y is 1, it implies that 4 exponent x equals 1, which is now very similar to our first example. But this time we have to express 1 in power of 4. So we choose 4 raised to power 0 to replace 1. By equating the exponents, we have that the first value of x is 0. Still standing on our existing relationship between x and y, when y is 16, it implies that 4 exponent x equals 16, which is 4 to the second power, or 4 squared. Therefore, equating the exponents, x equals 2. Hence, the exponential equation is true when x is either 0 or 2. One very good thing about solving this disguising quadratic equation is that sometimes either one of the roots of the quadratic equation or even both might just be negative. You really want to have one or both roots to be negative. It is lovely and cool. Let's see how cool that is in the next example. 25 is a perfect square, so we express it as 5 to the second power, or 5 squared. From the law of multiplication, we can rewrite 2 times 5 exponent x plus 1 as 2 times 5 exponent x times 5 to the first power, or just 5. It is beginning to appear that 5 exponent x can also be found in the first term by swapping the positions of exponents 2 and x, according to the law of power. Rearranging the middle term, 2 times 5 gives us 10. Let 5 exponent x be equal to m, since it is now common. Therefore, the new equation becomes m squared plus 10m minus 75 equal to 0. And after factorization, we have m minus 5 in bracket, multiplying m plus 15 in bracket equal to 0. The roots of this equation, therefore, are positive 5 and negative 15. Again, these roots are not the solutions to the original equation. We therefore fall back to our assumption or relationship between x and m. When m is 5, this implies that 5 exponent x equals 5, which is also written as 5 to the first power. So the first value of x is 1. For the second value of x, we just do nothing, because for all values of x, 5 exponent x is going to be positive. In other words, there is no value of x that will make 5 exponent x to be negative 15. That's totally impossible. So when one of the roots is negative, we say that there is no solution to x. And when both roots are negative, we say that the entire equation does not have solution. There is another important question we need to answer. Even though the roots are not negative, what if one or both are not perfect squares, perfect cubes, and so on? For instance, if 3 exponent x equals 7, we all know that 7 is not a negative number for we to say that the equation does not have a solution. Neither can 7 be expressed in power of 3 for we to equate the exponents. Let's see how to deal with such scenarios in the next and the last example for today. We have to first of all rearrange the equation to have 0 at the right hand side. By applying the law of multiplication to the first term, we have this as the new equation. Let 3 exponent x equal p, so that the equation becomes 3p squared minus 11p minus 4 equal to 0. The values of p after factorization are negative 1 out of 3 and 4. Back to our relationship between x and p. We already know that when p is negative 1 over 3, there is no solution for x. And when p is 4, it implies that 3 exponent x equals 4. In a scenario like this where both bases cannot be made to be the same, we take the natural logarithm of both sides of the equation. From the power law of logarithm, the power x falls down behind. And this now looks like every other normal linear equation. We divide both sides by log 3, and x equals log 4 over log 3. From the calculator, log 4 has an equivalent value of 0.60, and log 3 has an equivalent value of 0.48. Therefore, 0.60 divided by 0.48 is approximately 1.25, which is the only solution to this exponential equation. We encourage you to watch out for our next video on logarithmic equations. I really hope that this video is helpful. If it is, do not forget to give it a like, and if you want to see more videos like this, subscribe to our YouTube channel, turn on your notification, and share the video among friends. See you in our next video. Learn more at Math Key.